Hello students, welcome back. Previously we studied some elementary differentiation problems like these, and all these problems can be done with these rules only, along with some trivial rules of course. In any case, the key rule is the power rule here, that's 90%, probably more, and a special case log function, and even more special case natural exponential function. Now let's consider a little bit harder rule. Similar power rule, special case log function, and natural exponential, but unlike the previous case where we have straight up functions, we have a composite function ax plus b inside. Remember, x to the k power versus ax plus b to the k power, x to the negative first power versus ax plus b to the negative first power, e to the x power versus e to the ax plus b power. Ax plus b inside. And the result, we have 1 over a popping up all the way. Let's take a little bit bigger font so that you can see this 1 over a better. You see, 1 over a here, 1 over a here, 1 over a here, and so on and so forth. How do you get that? Let's start from the right hand side and take the derivative. Now plus c will be gone because that's just constant. And then here's a coefficient. So coefficient stay the same, I can pull it out, times the derivative of this. So how do you calculate the derivative of that? Multiply by the power and subtract 1 from the power. That's it, isn't it? One more actually. By chain rule, we have to multiply the derivative of the inside. And that is this a, which will divide this one out and disappear. And this k plus 1 and that k plus 1 will kill each other off. And what's left in the end is going to be just ax plus b to the k power. And that's precisely where we started. So from the right hand side, take the derivative, we end up with this. And this whole thing works when k plus 1 is non-zero. When k plus 1 is 0, then you're going to get this computation. I'm going to leave that to you. And this too. The reason we get 1 over a is because of this right here, the chain rule. We have to undo that chain rule. If you remember this theory, that's great. Even if you do not remember all those, you can still use these. Let's go ahead to a problem. I'll leave the first problem to you. Let's go to the second problem. This is, as a matter of fact, a power form like this. 2y plus 3 to the what power? Negative, because it's coming from denominator, and we have square root, so 1/2 power. So it's not reciprocal function. You're not going to get log function. If you focus on a negative first power, you're going to get this form for k equals negative 1/2. And let's go ahead and apply this rule. Let's see. This one, 1 over a. So 1 over 2 times, and then let's see, 2x plus 3y, 2y plus 3, excuse me, and then add 1, and then you have to multiply by reciprocal. Add 1 and divide. That's the end of the problem. If you simplify this, you can write like this. I guess that's it. Okay, that's it. Here's the wrong solution, by the way. If you focus too much upon reciprocal, you may end up getting a log function. And the best way to protect yourself from that kind of mistake is to focus upon negative first power instead of getting formula like this. You see, if you focus upon reciprocal, then you may end up making the same mistake that I just mentioned there. Log of square root, kind of like that. But if you focus upon negative first power, no problem there. How about the next problem here? We have some denominators and so on, so shall I take bigger font? Okay, all right. And this too. One half power. And now that I have 1/2 power and the 3z plus 4, this too I'll simplify as negative first power as a power form. So instead of just breaking up and folding out this square root and fraction expression, I'd rather break up this power expression. Okay, parenthesis open. And then first is 1, and outside 1 times, so this negative 3z plus 4 to the negative first power. And then inside 3z plus 4 to the 1/2 power. And last, oh, by the way, I'm running out of space here. Okay. Last. So this times that 3z plus 4 to the negative 1/2 power. 1/2 negative 1, so that's what we get. Did I do this right? First, 1 times 1, no problem there. Outside, 1 times this. Okay. Inside, this times 1. Alright. And last, 1/2 power, negative 1 power. So negative 1/2 power total. Okay, alright. Antiderivative. Antiderivative of 1 is z. Antiderivative of this negative first power is log 3z plus 4, and then we need 1/3. Remember? Okay, now this one, 3z plus 4 to the add 1, so 3/2 power, so I need 2/3 power, oops, 2/3 power, and then that's not enough, I need this extra 1/3. You see, extra 1/3, extra 1/3. How about this one? Ooh, 3z. It's similar. 3z plus 4, add 1, so 1/2 power. So reciprocal. But that's not enough. I need 1/3 power. Not 1/3 power, excuse me. 1/3, which comes from this 1 over a. See? This 1/3, and this 1/3, and this 1/3, they're all coming from the same 3 here. And I guess you can stop here, but if you simplify this and then get 2/9 and then 2/3, that's acceptable too. Let's see, what did I do here? Oh, I couldn't write everything over here, so let's take regular font. Yeah, all the same, except that typo here. Character should be Z, not X. Sorry about that. Okay. So of simplification, and then 2/3. There you go. So that's a bit simplified version, but the last line is unnecessary. As far as I'm concerned, that's unnecessary. You can stop at the third line. Anyway, a bit harder problem that required a bit of an algebra foiling out. But in any case, you have to use this 1 over a, 1 over a. Not this one yet, you use both of these two. How about the third rule? Well, looks like we have some exponential problem coming up, so it looks like we'll have to use that. They'll have to wait. Let's stop here, and then let's do the other two problems in a separate video.